Have you ever stopped to think about how scientists actually count atoms? I mean, they're impossibly small, and there are just so many of them. Well, it turns out they have this absolutely brilliant trick up their sleeve. It's kind of like a secret code that turns a totally impossible task into simple math. Okay, let's dive in and crack this chemist's secret count.
So to get our heads around this, let's start with something a bit more tangible. Imagine I just handed you a massive bag, and I told you there's 1,000,000 coins inside. How on earth would you figure out the exact number?
I mean, counting them one by one? You'd be there forever, right? Just, it's not going to happen. But what if I told you there's a super elegant shortcut, a way to get the exact number in just a couple of seconds without counting a single coin?
And that shortcut is all about one simple but incredibly powerful idea: counting by weighing. Yep, it's a way to figure out how many by asking how much does it weigh.
The logic here is just so clean. All you need to know is the mass of one single coin. Let's say it's 2 grams. Then you just weigh the whole bag, say 500 grams. A little division later, 500 divided by 2, and boom, you know you have exactly 250 coins. It's fast, it's accurate, and you didn't have to do any of that mind-numbing counting.
And here is the absolute best part. This very same logic, this awesome little shortcut, is precisely what chemists use to count atoms. They count the uncountable by putting it on a scale.
So how do we take this idea and apply it to the world of chemistry? Well, chemists basically have the same problem as our coin counter, but, on a completely cosmic scale. They needed a way to group atoms into standard, easy-to-handle packages.
Think about it, right? We do this all the time. We have a dozen for eggs, a ream for paper, a 6-pack for sodas. They're all standard packages that just make life easier. Chemists needed their own version for the atomic world. They needed a chemist's dozen.
And that standard package has a name: the mole. Now, okay, the official definition sounds a little technical, but the big idea is actually pretty simple. It's just a specific, agreed-upon number of particles. It's the number of atoms you'd find in exactly 12 grams of carbon-12. That became the gold standard for counting in all of chemistry.
So, what is this magic number? It's that. Just look at it, 602 sectillion. It's a number so huge it kind of breaks your brain a little, and that's how many atoms are in just 12 little grams of carbon.
This monster of a number has a name, the Avogadro number. And that, my friends, is the chemist's dozen. 1 mole of anything, doesn't matter if it's gold atoms, water molecules, anything, it always contains this exact number of particles.
So let's see how this all lines up. With the coins, the package was the bag. For atoms, the package is 1 mole. The count for the coins was 250. For atoms, it's that giant Avogadro number. And the total weight of the bag? For atoms, that's what we call the molar mass. See? It's the exact same idea, just with different labels.
Okay, so we've got this concept of the mole. That's great, but how do we actually use it? This is where we move from just counting to actually calculating. This is where the real work of chemistry happens. The absolute key to all of this is molar mass. Remember how we needed to know the weight of 1 coin? Well, chemists know the weight of 1 mole of pretty much any substance. That is the weight of the package. You can just look it up for any element or compound. It's a known value, and we measure it in grams per mole. And this is what connects the whole thing. It builds a bridge, a direct path from the mass of a substance, something you can easily measure on a scale in a lab, to the exact number of moles, the exact number of packages that you're dealing with. And it all comes together in an equation that is just as simple as our coin problem. If you want to find the number of moles, you just take the mass that you measured in the lab and you divide it by the substance's known molar mass. That's it. That's the link between the big world we can see and measure and the tiny atomic world we can't. And that right there, that's the real magic trick. This simple little formula lets chemists do something that sounds totally impossible. They can measure out a precise number of atoms, we're talking trillions and trillions of them, just by weighing some powder on a scale. So why is counting atoms this way so important? Well, because chemistry, at its heart, is all about building new things, new molecules. And to do that, you absolutely need a reliable recipe. You see, a chemical equation, it's not just a bunch of random symbols on a page. It's a recipe. It tells you exactly how many packages, how many moles of each ingredient you need to combine to get the perfect result.
Let's take a super classic example: making water.
The recipe is crystal clear. It says you need 2 moles of hydrogen gas to react with exactly 1 mole of oxygen gas. You mix them together in that perfect ratio, and what do you get? 2 moles of water. The mole is the cup or tablespoon in this cosmic cookbook.
And this brings up a really practical question that every cook and every chemist has to deal with. What happens if you're following a recipe, but you run out of one of your ingredients before you run out of the others?
Let's step out of the lab and into the kitchen for a second. Let's make some sandwiches. Your recipe is simple. 2 slices of bread, 1 slice of cheese. Now you look in your fridge. You've got 10 slices of bread, but only 3 slices of cheese. So how many sandwiches can you actually make? Well, you've got enough bread for 5, sure, but you only have enough cheese for 3. The cheese runs out first, which means you can only make 3 sandwiches.
In chemistry, that ingredient that runs out first, the cheese in our example, has a special name. It's called the limiting reactant. And it's so important because it's the thing that decides the absolute maximum amount of product you can make. Once it's gone, the reaction just stops. Doesn't matter how much of the other stuff you have left over.
So, when you put it all together, why does the mole matter so much? Because it's the one concept that turns chemistry from just kind of mixing things together and seeing what happens into a precise predictive science. It's what allows us to design and create the modern world, everything from life-saving medicines to the advanced materials in our phones, because we can follow an exact recipe, knowing precisely what to put in to get exactly what we need out.
And that leaves us with one last thought to chew on. This whole incredible system for counting atoms started with a really simple, clever idea: counting by weighing. It just makes you wonder what other impossible things are out there, waiting for us to measure or understand them, if only we can find the right clever shortcut.